Over the next few topics that we're going to talk about, we're going to be focusing on second order linear differential equations. So equations that generically have a form something like this, like, a2 of x y double prime plus a1 of x y prime plus a0 of x y is equal to some function of x. So this is a second order linear differential equation. These, in this case, would be non-constant coefficients. I mean, they could be constants, but they also could be functions of x. And since it's equal to some function, in this case, this is non-homogeneous. Now, generically speaking, for a lot of these we're going to look at over the next couple of classes, most of them are going to start out homogeneous, so equal to 0. And even if they're not homogeneous, we almost always want to write the lead derivative by itself. So always divide through by our lead coefficients, whether it's homogeneous or not. And we're going to get an equation that looks more like this. Y double prime plus P of x y prime plus Q of x y is equal to, now I'm going to call this some other function of x. I'm going to go ahead and change this back to big F of x up there. So, right, it would change if we divided through by whatever our lead coefficient is. Now, this is more the form that we're going to take a look at these types of equations for the next few topics. Second order linear differential equations, in this case, homogeneous or non-homogeneous. Now, reduction of order is a method for finding a solution to an equation like this if you already happen to know one solution, which in a lot of cases you would know a solution if you're designing your differential equation to model a real-world problem. You might actually know what a solution is to start with. Now, since this is a second-order differential equation, we know we need two linearly independent solutions. So if you have one linearly independent solution, can you find another one? So this is to find a second linearly independent solution if you know the first, or one. Okay, here's the idea. Remember what linear independence means. The idea is basically one function's not a constant multiple of another function, which means we know, let's say y1 is a solution. Well, we also know that the other solution, y2, don't write this down, cannot be a constant multiple of y1. Well, since it can't be a constant multiple of y1, that means that y2 has to be some function times y1. Now, since our independent variable is x here, the way that we have this written, we're going to assume that the non-constant multiple, of course, is a function of x. So this has to be true if y1 and y2 are going to be linearly independent. So can we use this fact to figure out what mu is? And if we can figure out what mu is, then we can figure out what y2 is because, well, we know what y1 is. All right, so we can actually get to a formula here that tells us exactly what the second solution is and shows you the foundation of what the idea behind reduction of order is. So this is going to get a little bit messy. Let's do this. Let's say that this is our solution. So let's take all of our derivatives and plug it into this equation. Now, for simplicity's sake, I'm going to go ahead and only worry about the homogeneous one because we're looking for the second solution to a homogeneous equation. So in this case, this is the equation we're looking at. So if I'm going to plug that into here, I'm going to need the function. I'm going to need its first derivative. Of course, here I'm going to drop the function notation. We're going to need to do the product rule. So mu prime y1 plus mu y1 prime. And come on, I'm also going to need the second derivative. So I'm going to have to do the derivative of this. Now I'm going to have to do the product rule twice. That's mu double prime y1 plus mu prime y1 prime. That's the product rule for the first piece. Plus the product rule for the second piece is mu prime y1 prime plus mu y1 double prime. Now notice here in the middle, these two can combine here because those are the same to give us two of them. So I'll do that when I move it up here. So what am I going to do? I'm just going to plug it into this differential equation because y2 has to be a solution. So I'm going to do y2 double prime plus p of x y2 prime plus q of x, y, 2 has to be 0. So y double prime, we just did that a second ago, that's mu double prime y1 plus, and we combine our like terms there in the middle, that's mu prime y1 prime plus mu y1 double prime plus p of x times our first derivative. So that's going to be mu prime y1 plus mu y1 prime plus q of x times, well, mu y1. Now all of this, since we're looking for the two linearly independent solutions to the homogeneous equation, have to be equal to 0. All right, let me go ahead and distribute everything out. So this is mu double prime y1 plus 2 mu prime y1 prime, mu y1 double prime. Now I'm going to drop the function notation for p and q just for ease sake. So that's p mu prime y1 plus p mu y1 prime plus q mu y1 equals 0. Okay, now for simplistic sake here, let's see. I'm going to group by, let's say, I don't know, let's group by derivatives on mu. Here's what I mean. Let's take a look at this. How many mu double primes do I have? I have mu double prime y1. Well, that takes care of all the second derivatives of mu. What are the first derivatives of mu? Well, here I have a first derivative. Here I have a first derivative. So this would be mu prime would be 2y1 prime plus this one. This would just be p of x y1 plus, and then what do I have from, let's see, we took care of the first derivative. So that one's that one and that one. Now just for mu's, what do I have? I have these three terms left. So this is y1 double prime plus p of x y1 prime plus q y1 is equal to 0. Okay, so you're like looking, well, that didn't make things any nicer, but it actually did. Something really, really nice happened here. By the way, we did those last three. Remember, we know that y1 is a solution to this equation, which means if I plug y1 into this, it has to be equal to 0. So y1 double prime plus py1 prime plus qy1 has to be 0. Notice that's exactly the last piece that we have here. All of this has to be 0 because y1 is a solution, which means this simplifies to mu double prime y1 mu prime 2y1 prime plus py1 equals 0. So it greatly shortens that equation. Now remember where we're going. We're trying to figure out what this function mu is so we can figure out what y2 is. So now we have a second order differential equation in mu, because we know what y1 is, so we can figure out what the rest of this stuff is. But notice now, since the no derivative canceled, all we have is the second derivative and the first derivative, which, if we did just a real quick substitution, and this is where this method gets its name right here, let's let another variable, I don't care what you use, let's let z equal mu prime. Well, then it should be obvious that z prime is mu double prime. So by plugging that in, I would get z prime y1 plus z2 y1 prime plus p times y1 is equal to 0. This is more of a visual thing than anything else. Notice what did we do? By doing this, we reduced the overall order of this differential equation. Technically, it's still the second order, but we've hidden it behind this substitution. Now this looks like a first order linear differential equation, which means we could go about solving it the way we did before. The first thing you want to do is get that first derivative alone, so I'm going to divide through by y1. So if I divide through by y1, I get 2y1 prime over y1 plus p is equal to 0. All right, so I divided everything by y1. So I know it's a little confusing, but this is like our y prime plus p of x y equals 0. So we can use an integrating factor for this. My integrating factor is e to the integral of whatever's in front of the dependent variable. So this is 2y1 prime over y1 plus p of x dx. Well, the first one, the derivative over the function, that's just a natural log. And since we're joined by plus, I'm going to integrate each one separately. So this is going to be 2y1 prime over y1 dx times e to the integral, I'm going to put that back, p of x dx. Well, this is just a logarithm, so this is e to the 2 times natural log absolute value of y1. And since I don't know what the original p of x is, that has to stay the same. Now, lucky enough for us, on this side, this thing simplifies nicely. We can bring up the exponent, we'll get rid of our absolute value, and then we can get rid of the logarithm. And after all that work, that's what we end up with for our integrating factor for this first order linear differential equation. Now, for room's sake, I'm going to go back this way. Now remember what we need to do. To use our integrating factor, we multiply through the entire equation by the integrating factor, then integrate. On the left-hand side, we always get the integrating factor, that mess, times our dependent variable, where our new dependent variable is z. So on the left-hand side, I'm going to get z, y1 squared e to the integral of p of x dx. On the right-hand side, I'm going to multiply and integrate. Good news for us, that's 0. So we get y1 squared e to the integral of p of x dx, and the integral of 0 is just an integration constant, so we get some c here. So this is easy enough to solve. Z is equal to some constant divided by y1 squared e to the integral of p of x dx. Now, for some reason, and I'm not sure why, just kind of go along with it, most textbooks at this stage write it like this: some constant e to the negative integral of p of x dx all over y1 squared. For some reason, they tend to like to move the exponential to the top, so I'm just doing that one step there to kind of match what you're going to see in your textbook. Well, we're really close to being done, air quotes, being done here, because now I can figure out what mu is, right? Because I know what z is. So z is equal to mu prime. So mu prime is going to be equal to c e to the negative integral of p of x dx all over y1 squared. And we need some more room. We need some more room, so all we got to do now, of course, since that's a derivative, is integrate both sides here. So our mu of x is going to be the integral of some constant, we'll talk about that in a second, negative integral of p of x dx all over y1 squared dx. All right, a few things that we need to talk about. Remember, that's just mu. So y2 is going to be equal to, by definition, what we said a second ago, mu of x times y1. So y2 will be y1 times the integral c e to the negative integral of p of x dx all over y1 squared dx. Now, when we're talking about the fundamental set of solutions, we said that any constant multiple of a solution was still a solution. So we have this constant multiple in here that we really don't need anymore because we're really looking for the fundamental set. So most of the time, we just let that arbitrary constant right there be 1. So I'm going to kind of cheat and just erase it. Because remember, we're just looking for the fundamental set. So any constant multiple will work, so we can get rid of any arbitrary constant. Now, another small detail. When we do integrate this piece here, we get an arbitrary constant, right? So don't write this down, this is just me. We'd have y1 times whatever this is, so this would be some function of x plus a constant. Well, if you take a look at this, you have y2, that'd be y1 times whatever that is, plus some constant times y1. Remember how we make our general solution. We do a linear combination of our fundamental set. So this would be some c1 times y1 plus c2 y2. Well, if I put this in for y2, notice what we'd end up with, we'd have another version of this piece right here. So by this integration constant you get from this integral only ends up just combining with the first solution anyway. So when you do this integral, you do not need the integration constant because it doesn't add any new information that we don't already have from this first piece of our linear combination. All right, now there's good news and bad news here. Good news is I did all this work, so you now have a formula. The bad news is you got to memorize a formula. And I tend not to like to memorize formulas, so I never actually use this formula to do these problems. I do it, air quote, the long way. Now, it's not that much longer, to be honest. It's just a few extra steps, and it gets you to practicing some of your old methods anyway. So when you're doing your homework, feel free to use this formula from time to time, but I'm going to show you kind of the long way that I generally work through these, and I want you to be able to do it this way as well. All right, so let's start out with, say, an easy differential equation. Air quotes around that when I say easy, just not complex. So let's say we got y double prime plus 4y is equal to 0. All right, this is a second order linear differential equation, and it is homogeneous. Let's say I told you y1 equals cosine 2x is a solution. All right, well, to find y2, we could just plug it into this formula right here, and you get to our answer. Everywhere there's a y1, put cosine 2x. Now in this case, remember our formula, I'll squeeze it here real quick, is p of x y prime plus q of x y is equal to 0. P of x is the function in front of the first derivative after you've divided through by the lead coefficient. So in this case, our p of x is actually 0 in this case. So that's what you would plug in for that. All right, but we're not going to use the formula. We're going to use this idea that y2 is some function times y1. So y2 is equal to mu times cosine 2x. Now to plug into this to find our solution, I'm going to need the second derivative. So just like we did when we developed this, we're going to take the derivative. Of course, our product rule there, then y2 double prime is going to be mu double prime cosine 2x minus 2 mu prime sine 2x. Okay, that gives us the derivative of our first term here. Now we're going to do the product rule for this as well, so that's negative 2 mu prime sine 2x. And then the derivative of the sine piece, that's going to be minus 4 mu cosine 2x. Now again, just for time's sake, you can see that these two in the middle there will combine. All right, so let's plug it into our differential equation. So we're going to put y2 double prime plus 4 times y2, and that's got to be equal to 0. So y2 double prime gives me mu double prime cosine 2x minus 4 mu prime sine 2x minus 4 mu cosine 2x. Okay, that's our second derivative, plus 4 times y2. y2 was mu cosine 2x, and all that has to be equal to 0. Now at this stage, when you're actually dealing with functions, you should have some type of cancelization happening. And notice we do here, right? Those two pieces go away completely. Basically, at this spot, after you combine like terms, if you had any terms that still had just mu in them, you've made a mistake. Go back and find it. Okay, so we're left with this, mu double prime cosine 2x minus 4 mu prime sine 2x is equal to 0. Remember, we're trying to solve for mu. So I don't have any no derivatives, so I can do a substitution to reduce the order of this to a first order differential equation. So some letter equals mu prime, so the derivative of that is mu double prime. So I get z prime cosine 2x minus 4z sine 2x is equal to 0. Well, this is a first order linear differential equation. So we divide through by our lead coefficient. Now, again, anytime you divide through by a function of x, you want to make sure it's not 0. And of course, cosine can be 0. So just a quick little thought. this solution is only going to be good when cosine 2x is not 0. Okay, so when we divide through by that completely, we get z prime minus 4. I'm going to go and write this as tangent 2x z equals 0. Okay, first order linear differential equations, we're going to use an integrating factor. This piece over here is our p of x. So let's sneak this in over here. Our integrating factor is going to be e to the integral of negative 4 tangent 2x. All right, well, for both of these, you would do a u-type substitution. Of course, the 2 is going to give you a half when it comes out, and the integral of tangent is a negative log of cosine. So this ends up being 2 natural log absolute value of cosine 2x. Or you can bring up the exponent or just cosine squared 2x. So make sure that you can do the integration between those two spots. Okay, so that is our integrating factor. So when we multiply through and integrate, on the left-hand side, I get the integrating factor times the dependent variable. On the other side, we multiply and integrate. Of course, on that side, times z, we just get some constant. Now you have to hold on to this constant for a little bit, because, or you can put a 1 there if you want, because we need something over there. It can't be 0, because that would make everything just z being 0, which means we would get what's the trivial solution to this. So by moving that over, we get z is equal to, if I divide both sides by cosine squared, well, 1 over cosine is secant squared. Okay, well that's what z is. We really don't care what z is, we're trying to figure out what mu is. So let's go ahead and let me get my integrating factor here out of our way. A little bit of side work. So that means that mu prime is some constant secant squared 2x. So mu is going to be equal to the integral of some constant, we can pull that out, secant squared 2x dx. Now at this stage, if you wanted to drop that constant or make it 1, I'm okay with that. So the integral of secant squared is tangent, right? So of course we're going to get a 2 from here, but that kind of goes into our arbitrary constant. So mu is going to equal some c over 2 tangent 2x. Now again, so I'm just going to say my integrating factor is just tangent, or my function here is tangent 2x. So now that we know what mu is, we can now figure out what y2 is, because y2 is equal to mu times y1. So y2 is equal to the tangent of 2x times y1 was like cosine 2x, which simplifies, the cosines will reduce, so y2 is just sine 2x. So our fundamental set of solutions for this particular problem would be cosine 2x and sine 2x, which means the complementary solution, or solution to the homogeneous equation, which it was homogeneous, would just be a linear combination of these. So c1 cosine 2x plus c2 sine 2x. All right, so using reduction of order is a very nice method to find a second solution given a first solution, which is going to pop up from time to time. We're going to see it a few more times as we go through this course. So you're welcome to, like I said, you're welcome to use the formula that I derived for you. It's quicker than this, but make sure that you can go through all the steps here, because it is building some of your basic skills that you're going to need throughout the entire semester.